Okay, we're going to look at rates of change. This is an introductory video, and we're starting a journey here which will won't end in calculus, but one of the destinations will be this thing called calculus and finding the derivative. And it's a very exciting study in mathematics, so that's one of our destinations. It's a little way away yet, but when we get to calculus, we'll first talk about the derivative, or the process of differentiation. But we've got to understand a few principles first, and we're going to link back to what we already know about rates, or rates of change. So we know about rates, we see them each day, and you might see somebody's typing speed, words per minute. You might know the price, cents per litre for fuel. You might go into the supermarket and see dollars per kilo for fruit. You might see on a car speedometer kilometres per hour, kilobytes per second with data. So we notice that these things are basically comparing or putting one quantity versus the other. So we have quantity 1 changing compared to quantity 2. So sometimes people say it's like a comparison of things with a different unit or unlike things. So that makes it different to a ratio. So rates are about change. Sometimes we refer to things as such as rates of change. That's a common phrase you'll hear, rates of change. And it's how one quantity depends on another, and it's about how one changes in comparison to the other one changing. Some things change constantly, which might sound like I'm using contradictory language. Changing constantly, but constant rate of change is a thing. Constant, I'm going to use ROC to save my writing, ROC, rate of change. Constant rate of change, the graph of that would be a straight line graph. Now, for every change in the independent variable, which I might call x here, and the dependent variable changes by a certain amount, and that stays the same. So if you go across a certain number of units, you'll go up a certain number of units in y. If we go across the same amount of units again in the x direction, we'll go up the same in y. So basically it's a comparison of how far we go up for every unit we go across. And you might have heard rise and run, and essentially that's what it is. It's a comparison of the rise and the run. Now you know that as the gradient. So for a graph of a situation where we have a rate of change of one quantity up against another, we're actually looking at the gradient. Now for a constant rate of change, we have a constant gradient. That line there, drawn in black, has a constant gradient. It's a straight line. Straight lines have a constant gradient, so therefore it has a constant rate of change. That's a special case. So straight lines give a constant rate of change, whether it's up or down or even horizontal. So that line there has a negative rate of change. So even this purple line here, it doesn't rise at all, does it? The rise is 0. The run, it has a run, it goes across, but the rise is 0. So it's got a constant rate of change. The constant in this case is 0. So it's a constant function, we would call that. So rates of change can be graphed, and that's a good way to analyze them. It's not the only way by any means, but the gradient is a key factor in here. So what we have here is something a bit more sophisticated. So the boldest line there is the actual functional relationship that we're looking at. So I'll go over that carefully in orange. There we go. It's a little bit wobbly. I'm sure you'll forgive me for that. We've got basically two other lines there. One's called a tangent and one's called a secant. And we're going to, tangents and secants are straight lines. A secant cuts through a curve in two spots, just like a secant in a circle is an extension of a chord. You might remember with circular geometry, that's a chord. If I extended it out in a straight manner, that's a secant. Same works if we don't have a circle, if we just have a curvy graph. And the secant, it goes through 2 points and it's a straight line. The tangent, however, touches only at one point on the line, there. So the tangent actually touches at 1 point only. 1 point of contact. This has 2 points of contact. So if we want to know we said the rate of change of this orange line, the answer is it's got lots and lots and lots of rates of change, an infinite number you could ask, because it's a curve. So it's not a straight line, this one. So wherever you look at it, its gradient will be slightly different. Now how do we know that? What we can do is look at a point of contact. Let's say at x equals 3, we would draw a tangent, which you can see pre-drawn for you, and at that 1 point only, that point and that point only, the gradient of the tangent would be the gradient of the curve, just for that 1 point. If you moved either side, it would change. So its rate of change equals the gradient, which is letter m, of the tangent, which I'm putting down as little t. So the rate of change is the gradient of the tangent. Now, tangents by hand are very, very hard to draw. Sometimes we can draw a secant and estimate the rate of change at the point by drawing a secant. The trouble is, you can see that the 2 points of the secant, one can be on the point we're interested in, but the other one might be a long way away. And that means it might be inaccurate. How could we improve this? So I'm just using Wolfram's demonstrations project, and it's an actual project called the tangent line problem, and the author of it is down the bottom there. Authors, contributors. The demonstration shows we can just choose all sorts of functions. I'm just going to choose x squared, so we've got the line y equals x squared. You can see that there in blue. And what we have is what we just saw. We've got a point Q where we're interested in finding out what the rate of change of the blue line is. In other words, the gradient at that point. Now, it's very hard to draw a tangent by hand, okay? So one of the things we can look at doing if we are using by hands is to draw a secant, as we just mentioned. Of course, if you look at the secant slope, and just by looking at it, and the tangent slope, the secant is this sort of greenish, brownish line, and the tangent is the red line. You can see they're obviously different. Don't even need to put any numbers on it. They're different. But of course, we don't have to necessarily take the other point of the secant where it is. We can bring it in closer, like that there, and maybe a bit closer again. And what we see is that the gradient of the tangent and the gradient of the secant get closer and closer. Now think for a minute, what would be the perfect, maybe even pause the video, what would be the perfect scenario? Have you got it yet? Well, the perfect one would be when P and Q are on top of each other. That would be a secant that actually becomes the tangent. Why not just use that? Well, if you're calculating with the methods that you know already, we're talking about gradient of a straight line, and we're talking about rise over run. Now, rise over run, okay, well, the trouble is that the run will be 0, because when we bring these aligned together, the run is the x distance, the distance horizontally on this diagram, and it's 0. You can't divide by 0, so there's a problem there. Wonder if there was another way, and that's what we're going to learn as we go through this unit. So there's just some introductory ideas, and maybe that's even generated more questions and answers this video, which is great, but it isn't just an introduction, and hopefully it's aroused your curiosity. So we'll see you in class.